All right, there we go. We are now recording. Before we get started this morning, your assignment 2 grades are out. All right, so take a look at those if you haven't already. There's some feedback with those. If you have any questions, contact first the TA who graded your assignment, because they can give you the most detailed answers on their feedback. And if there's any issue, please let me know. Right. But I've looked over them too, and I didn't really see any major problems. In general, people did pretty well on the assignment. But take a look at that and let us know if you have any questions. Now, today, we are, of course, officially done with all of the course content, but there is the exam next week. And so the goal today is to talk about the exam and to review the practice tests that we put online. So let's just dive into that. Now, a little bit of information. Of course, because we're still in Corona mode, the exam will be online. It's going to be next Thursday, March 18th from 8:30 to 12:30, although you'll have until 1 o'clock p.m., the extra half hour or so, just to make sure you can submit your assignment and get that in on time, but no later than that. It will be a Canvas assignment, but there's a separate Canvas page. Those of you who have registered for the exam have been invited to join that Canvas page and should have seen the invite by now. If not, log into Canvas, double check, make sure that's there. It will be put up as an assignment. It will be available at 8:30 that morning or around that time, a little earlier probably, and must be submitted by 1 p.m. Throughout the time, I will be available by email to answer questions. Right now, of course, since this is an online exam, we can't really stop you from looking at the book, looking at slides, looking at online resources, talking to each other. We can't, lock you up and prevent that necessarily. So, the thing is answers must be your own, and we will notice if you're working together. If you turn in very similar answers to this exam, we're going to have questions. Most questions are fairly open-ended, as you saw in the practice exam, right? So don't work with others, work by yourself. Don't copy answers from slides, from the textbook, from the internet. We're going to check for plagiarism, and we will notice. So do the test yourself. It's not going to be horrible. If you've been paying some attention, you're going to be fine. Right now, to help prepare for this exam, there's a practice exam on Canvas. It's been up for a couple weeks now, and we're going to go just question by question and just talk through the answers to that. And of course, this is probably going to run a little long. I'll warn you now, right? We'll just keep going until we're done. And I'm also happy to answer more questions afterwards. If you have questions in any course content, if you have questions on the homework, anything like that, we'll deal with that too as we go along. Now, feel free to throw things into the chat as we go, or we can also take some time at the end or this afternoon to answer questions, right? Now, before we get into this one by one, here's all the topics we've covered in the course, right? 14 or so lectures. Here's basically everything we've covered. The most important things are in bold, right? Anything is fair game. And anything is fair game. So look over everything. But the most important things are probably the very things that we've had exercise sessions about, those Friday exercise sessions. And those are the things in bold here. So quality, look over those quality attributes, be ready to write quality scenarios. That's going to be there, right? After that, we got into some testing concepts and then each testing phase. So we spent some time in system testing. We talked about 2 different methods of selecting system level test cases, the category partition method and then combinatorial interaction testing. Of those 2, category partition method is the most important. That's where you selected those choices, then represented the values for each, and then those if, error, and single constraints to limit the number of test specifications you can build, right? So this is a very general process for test creation. Exploratory testing. Those are those tours that you use as a human interacting with a system to help guide your efforts as you go through and interact with system behavior. Unit testing is incredibly important. Expect something about unit testing on there, right? Where we take a single class and we test its functionality in isolation from the rest of the system. We talked about structural coverage as a way to augment your test suite by targeting specific structural elements like certain if statements and making sure they evaluate to the right outcomes. And we talked about both control flow based metrics like statement and branch coverage, where you look at the way that control passes through the program. We also talked about data flow criteria, where you look at where variables are defined and then where those definitions are being used. Both of those are important. Just in general, know about structural testing. Mutation testing, where you purposefully put faults into the code and then see if your tests detect them. And if they don't, add additional test cases. That's another way to strengthen your test suite. So collectively, structural coverage and mutation testing are this embody this idea of test suite adequacy, where we can somehow measure how good our tests are and then use those checklists to help plug the gaps in our test suite. We talked about automated test case generation, which is often based on these measurable factors like structural coverage or mutation testing, where we used search algorithms and optimization algorithms, like a genetic algorithm like simulated annealing, in order to create test cases for a system based on things like attaining rapid code coverage. We talked about testing using models, and we finally concluded by with what's called finite state verification, where we take those models and we prove certain properties hold over them. That's, you're doing that currently in your homework right now. All right, so that's everything. Not everything, will be as each, it's not one question per topic on the test, right? The test is not going to necessarily be 15 questions long. It's going to be more about 9 or 10 questions long. So the practice exam is much longer than the real exam, much longer, right? I just gave you a lot of questions on it just to make sure you're prepared. So it's not necessarily one question per topic, but most of these topics will be at least on there in some form. Be familiar with them. Focus probably most on the bolded things, but don't forget about the non-bolded things either. Now, before we go question by question through the exam, are there any questions from you? Everyone good this morning? Give me a chance to get a drink of coffee. All right, cool. So let's do this. So I open with a bit of multiple choices warm up. All right. And now on the multiple choice, more than one answer can be correct unless it's true or false, in which case, it's not both. But for anything with more than 2 choices, multiple choices can be correct. Select all that apply. There will be some warm up on the real exam, more multiple choice along these lines, though of course different questions. So go read these over carefully. The wording is definitely an important part. This is basically a way just to wake up and focus your mind a little bit. So one by one, a program may be correct yet not reliable. True or false? Right. Well, that one is true. A program can be correct but not reliable. Now, what does that mean? Well, that means that it might be correct with regard to our specification, right? We have a set of requirements. That set of requirements says everything is fine. We prove it is. But then when you start actually running tests on the system, and we see the system start to fail when it's placed outside of its operational boundaries. Now, if a system is on average down for a total of 30 minutes during any 24-hour period, which of these are true? Well, its availability is about 98%. Its reliability is about 98%. Its mean time between failures is 23.5 hours. And its maintenance window is 30 minutes. So let's just break these down a little bit. It's down for 30 minutes out of 24 hours. So it's up for 23.5 hours. of that 24. So you can divide 23.5 by 24, and you're going to get something that's rounds about to about 98%. So that one is true. Now, why is the second one not true? Why is its reliability is about 98%? Why is that not true? Well, that is not true because that reliability is what we measure using these measurements. So availability is a measurement of reliability. But reliability in itself is not a measurement. We can't say reliability is 50%, 60%. We have to rely on one or more of these specific measurements, right? So that's why that one's not true. We can't say the reliability is 98%. We have to say something like availability or the probability of failure on demand, the rate of occurrence of faults, each of those. Mean time between failures is 23.5 hours. Well, that's not true because we don't know how many times it failed, right? Did it fail once at the 23.5 hour mark? If so, okay, yeah, that's okay. 23.5 divided by 1, right? But we don't know how many times it failed. We don't know when it failed. It could have failed 15 times for 2 minutes each, right? So we don't have enough information to judge the mean time between failures here. Its maintenance window is 30 minutes. Well, we don't usually count scheduled maintenance toward the downtime, right? Because we intended it for it to be down. This generally means that it was, it crashed and went down for 30 minutes of that day on average. Not that, that we had it closed for scheduled maintenance for 30 minutes. So that's not true either. It may have had a 30-minute maintenance window, but that doesn't generally get counted toward downtime. Now, like I said, as we go through, let me know if you have any questions. Were this in person, I'd probably actually, ask you, make you answer, ask you, make you answer. But I'm going to mostly just go through them because I have, 78 slides here, and I want to make sure we get through them sometime today. All right. Third, in general, we need either mock objects or drivers, but not both when testing a module. So if you think back to the unit testing lecture, we talked about the components of test automation, right? So when we write code-based test cases, what do we need? Well, a mock object is a case where we create a fake version of a class to substitute for a real class. We do this when either the real class has not been built yet or we don't trust it yet. So for example, when we're unit testing, we often create mock objects to substitute for the dependencies of a class. So when a class calls another class, the mock object doesn't do any real work. It just returns a static result. So for example, if you mocked a thermometer, it would always return 40 degrees or something like that. So when we're testing a module, the question is, we need either mock objects or drivers, but not both. So a driver is a test case, basically. A driver is any substitute for a calling program. So generally that's a test case because a test case sets up the program and calls it, right? Especially at the unit testing level, your unit tests are drivers, but it can also be any other code you have that basically is basically a fake interface to the system that calls elements of the underlying system. So when we're testing, the answer is false, which means we do generally need both, right? It's not really a one or the other situation. We always need drivers when we're testing because we need code to call the system. Mock objects, we don't always, but we often use those when we're unit testing as well. Right? Sometimes you will skip those. You will not have them in 100% situations, right? But we do generally want them. If a temporal property holds for a finite state model of a system, it should hold for any implementation that conforms to the model. The answer is true, and the key part here is the conforms to the model part. Okay? That's a big if. So if we prove a property over a model, that doesn't necessarily mean the property will hold in the real system. It only does if the model reflects the system accurately, right? So the implementation has to be built following the same interpretation of the requirements, and the model has to be detailed enough to capture what is happening when you run the real system. If that is true, and you prove a property over the model, then that property should also hold on the real system. And that's the thought process behind why you use finite state verification a lot of the time. It's a way to shape your requirements and analyze your requirements. It's also a way to gain some assurance that the system is going to work as well. But for that to be true, the implementation also has to conform to the model. So a test suite that meets a stronger coverage criterion will find any defects that are detected by a test suite that meets only a weaker coverage criteria. So if we have a test suite that achieves MCDC coverage, is that also going to detect the same faults detected by a test suite that detects branch coverage? And the answer is false. Now, the answer is false here because these criterion don't say anything about specific faults. What they do is they guide you to exercise the code in different ways, and the thought is that will increase your likelihood of detecting faults, but that doesn't mean you pick the same input. So you will only detect the same faults if you use the same input, right? Or very similar input that will trigger that specific fault. So if just because a test suite meets a stronger coverage criterion doesn't mean it's going to detect the same faults detected by a weaker criterion. In theory, it could detect more faults. In theory, it could detect certain harder to detect faults. But it's not necessarily the same faults unless you use the same test input. Now, a test suite that achieves MCDC coverage, modified condition decision coverage for a given program when it's executed, will exercise which combination of these at least once? Every statement in the program, every branch in the program, every combination of condition values in each decision, and every path in the program. Only the first two of these are true, right? So MCDC coverage says that we have to take every branching or take every Boolean statement in our program, right? So that will include all of your if statements, all of your for loops, or anytime you calculate a Boolean expression, it'll take all of those. It requires those Boolean expressions, those decisions as a whole, to evaluate to true and false. It requires that you break those decisions down into their individual conditions, and each condition evaluate to true and false. And it requires that you show each condition can have an independent effect on the outcome of that decision as a whole. So you hold the other conditions at a static value, you change the value of one condition, and when it changes, the outcome of the expression as a whole should also change. So if you have A and B, you would hold B as true and then flip A from true to false. And when you did this, the expression value changes, and that shows that A has an independent impact. You then do the same for B. So how does that work out in terms of these possible outcomes? Well, okay, when you go through and you evaluate every Boolean condition or every Boolean decision, that by necessity is going to cover every single branch in the program. Now, if you cover every branch in the program, you will also cover every statement in the program. So both of those are true. What about every combination of condition values? That's not true because we don't require that, right? There is one of these called compound condition coverage that we talked about very briefly, where you did have to have every possible outcome for every condition. So if you had two conditions, A and B, you need true and true, true and false, false and true, false and false. But for MCDC coverage, you don't need every combination of those. You usually just need some subset of them. So you won't cover that. And then every path in the program, you absolutely won't cover every path with MCDC coverage, right? Because we're not really concerned with that. We're concerned with one Boolean decision at a time. Everyone still with me? few more of these. Category partition testing techniques require you to identify the characteristics of parameters, representative values, the definition use pairs, or pairwise combinations. I think I might have actually changed that in the practice exam to say, choices or something, but in any case, it's still the first two of these. Why these? Well, you need to identify the choices when you're testing, right? That's the first part of this technique, in fact, is to take the functionality you're testing, look at its parameters. So, I mean, this is true for parameter characteristics. Look at its parameters, and for each of those, break that down into what you control when you test, right? Those are your choices. What do you have control over and can vary to get different outcomes for running this functionality? For each of those choices, we choose a set of representative values. Those are different types of input we can apply to change the outcome, right? That generally means things like your valid inputs and then different types of invalid input, things that can lead to erroneous outcomes. Def use pairs have nothing to do with this. We're talking about the system level. We're not looking into the source code. Def use pairs are a part of the source code. We do care about those when we're looking at coming up with test cases based on the code structure, but it has nothing to do with choosing our system level tests. And then pairwise combinations are not part of this one. That's part of combinatorial interaction testing, which is our other test selection technique. So that's the tricky part. That's not part of this one. All right, validation activities can only be performed once the complete system has been built. True or false? Well, that's actually false. So validation, keep in mind, validation is when we assess whether the system meets the needs of its users. Validation can be done using the system as a whole. That's our alpha and beta testing or acceptance testing, where we hand it out to the users and say, try this and tell me what you think. That's part of validation, certainly. But you can start validation early. Validation can occur with the requirements. Validation can occur with your architectural design. Validation can occur using your quality scenarios, which you often write during the design process rather than during the testing process. Validation can happen at any point where you can talk to a user and get some information from them. So validation starts during requirements elicitation and just continues from there, right? So next, statement coverage never requires as many test cases as branch coverage. So statement coverage, always fewer than branch. The answer is false. They could require the same number of test cases. Now, branch often requires a bit more, but not necessarily. Very often you can do it in the same number of test cases, but maybe you have to pick different input. All right, two more. Requirement specifications are not needed for generating inputs to satisfy structural coverage of the program code. Is that true or false? Well, true. You do not need the requirement to generate test input to achieve structural coverage. Structural coverage is based on the source code. It can be your list of test obligations, your goals for achieving. Something like statement coverage or branch coverage can be extracted automatically from the code with no additional information. And if we generate test cases designed to achieve statement or branch coverage, then we don't need any information from the requirements. We would need to know about the requirements to do things like write assertions if we want to create test oracles. That's going to need some information. But if we're just generating input and our goal is structural coverage, we do not need the requirements. All right, now a system that fails to meet its users' needs may still be correct with respect to the specification, safe to operate, robust in the presence of exceptional conditions, and considered to have passed verification, right? So a system can be correct without meeting the user needs because it's correct with respect to our requirements. Our requirements should reflect the user's needs, but they're not guaranteed to. The requirements are what we say that the program will do. The requirements can be written without ever talking to a user. So the system can be correct and not meet the user's needs. It doesn't have the functionality they want. It doesn't do what they expect. It doesn't work how they expect. It can be safe to operate, absolutely, but still fail to meet the user's needs. That just means nothing horrible happens. It can be robust in the presence of exceptional conditions, right? So even if it's placed outside of its operational environment, it's still working. Sure, like that still might fail to meet the user's needs, and it can pass verification because verification has nothing to do with the user's needs. That's validation. Verification just means that it matches what we promised in the requirements. Okay, some rapid fire there. Any questions so far? All right. So next, we're looking at the air traffic control for an airport. This was our first exercise session, right? Back when we were looking at quality. Air traffic control is a service that's provided by ground-based controllers, who are the users of the system. They direct aircraft on the ground and through controlled airspace with the help of the software. And the purpose of the software is to prevent collisions, to organize the flow of air traffic, to provide support and other information for pilots, basically to make sure planes don't run into each other. Now, the software for this offers a few features. It can monitor the location of all aircraft in the assigned airspace. It can communicate with pilots by radio. It can generate routes for individual aircraft. It can schedule takeoff for planes to prevent collisions. And it can alert potential collisions based on the current bearing of the aircrafts as they take off and travel around the airport. To prevent collisions, it applies traffic separation rules, which ensure aircrafts maintain some minimum distance between each other. And when it gives route advice, that can either be mandatory, so to prevent an imminent collision, you must do this, or advisory, basically saying, hey, look, this is probably going to be a safe route. We recommend you take it. From this, we want to identify a performance, an availability, and a security requirement for the software, and for each develop a quality attribute, a quality scenario. So let's go through these one by one. First, we have a performance requirement. Our performance requirement is the under normal load, which we define as being less than 500 aircraft in our airspace. The displayed aircraft positions shall be updated on the user's display at least every 50 milliseconds. So every 50 milliseconds, at least, possibly sooner, our display will be updated with the current positions of all the aircraft. All right, so let's develop a scenario based on this requirement. This is going to check the system responsiveness for displaying positions. We can merge our system and environment state here and just talk about them together so it fits on the slide. But the environment's working correctly. There's less than 500 tracked aircraft, and all the actual aircraft are being tracked. So in the physical environment, there's 497 aircraft or something like that. And in our environment, we are detecting all 497 of them. All right, they're all there. Our stimulus is that there's just an update of our system. So we have a 50 hertz update of our aircraft system. And when the screen refreshes, well, the radar and sensor values are computed, and the new position is displayed to the air traffic controller with a maximum error of 5 meters. So we've updated our display. The positions are updated. There's a maximum error in the positions of 5 meters. Now, what's our response measure? How do we judge where the quality attribute is being met of performance? Well, this process is going to complete in less than 45 milliseconds, 95% of the time. So most of the time, it's in less than 45 milliseconds. 99% of the time, it's going to be less than 50 milliseconds. So there's our requirement. And then we're going to allow a small margin here where there's an absolute deadline of 55 milliseconds. Okay. So vast majority of the time, we're good with respect to the requirement, but we are going to say, you know what, there's a little bit of margin there. If there's an extra 5 milliseconds, but never go past that. If you ever go past 55 milliseconds, this is absolutely wrong. The important thing here is largely in your response measure, right? This is performance. Performance should usually be a probabilistic factor. So that's our 95%, 99% of the time. Now, because because there's a safety concern here, if this is too slow, that's why I also put in an absolute deadline. You might want to consider that as well, but that's just additional details. It's a nice thing you can do for these safety-based or safety-conscious scenarios. But otherwise, I mean, I guess the most important thing here is that you have some judgment of performance, and usually we complete within a certain response time, and we state that probabilistically. Availability, so that's our ability to tolerate either recover quickly from a crash or to minimize downtime, or availability can also be how you prevent crashes from bringing the system down in the first place. So it's either how you prevent a crash or how you recover quickly from a crash. The system should be able to tolerate the failure of any single server, host, graphics card, display, or network link. So this is one for how we avoid downtime. This one is saying that that we're going to have some redundant hardware and we have failover if a problem occurs, and that's going to prevent the system from going down. So here we have a monitor display card is going to fail in a workstation. The air traffic control has a specialized workstation. It's basically what we're saying here is that there's a specialized workstation. This workstation has a graphic card that's gone down, and we're going to deal with that somehow. The system was otherwise working correctly under normal load, no failures, no relevant environmental factors here, but suddenly our graphics card dies. What do we do about that? Well, we're going to detect the failure within 10 milliseconds and route the display information through a second graphics card that we have in place with no user discernible change. The graphics card failure will be displayed as an error message in the bottom right-hand corner of the screen. So what we're saying is that there's a second graphics card. When the first one dies, we're going to switch over to it, and that the user should not notice any real difference other than the pop-up message the bottom right-hand corner of the screen saying that, hey, one of your graphics cards has died. Check that out at some point. And how are we going to judge whether this was effective at maintaining availability? Well, we're going to say there's no loss in the continuity of the visual display. The failover will occur with the visual warning coming up within 1 second. Right. So here we've placed a deadline on this saying, look, switch over. All right, so security. For security, we are demonstrating how the system responds to an attack or how it avoids an attack. In this case, we have a requirement saying the system shall maintain audit logs of any logins to the database containing sufficient information to identify an attacker. How do we show that's the case? Well, the scenario. We have an attack. The agent has gained access to the flight record database. The system is otherwise working correctly under normal load, and there's no relevant environmental factors for this case. And an external stimulus happens. What happens is a malicious agent obtains access to the flight record database through password cracking and downloads flight plans for commercial aircraft. We have a required response, which is an audit log will be updated with login and download information to support future prosecution of the user. And in that log, it's going to contain the time, IP address, and related information for the download. We're going to use this information in identifying and analyzing attacks. So security is a little different from the others. Security has no standard set of response measures. Generally, though, you describe how this is going to effectively maintain security or stop an attack, or in this case, allow you to identify the attacker. Our goal is, well, we had an attack. What do we do about it? Well, we're going to identify the person who did it so we can prosecute them. How are we going to do that? We're going to maintain this information. We're going to maintain the time, IP address, and related information for every download that occurs. Any questions on this? All right. Next question. What is the difference between response time and throughput? And describe a situation where a system could display excellent throughput but poor response time, and vice versa. So here we're talking specifically about performance. We're still talking about quality here. Response time and throughput are two different measurements of performance that we can use to judge the performance of the system. So what's the difference? Well, response time is the question of how long it takes to service any one request. It's from the client perspective, right? When I request something to happen, how long does it take to happen? Throughput is a question of how many requests you can process in a given time period. So response time is for a single request. I ask for A, it takes 5 seconds. Throughput is saying, hey, in an hour, how many A requests can you service? So throughput is from the server's perspective, looking at, well, how many clients can I possibly serve over this period? So why does this matter? Well, we could have a situation where several different processes are working together to solve a particular problem. And we can process large volumes of transactions. We can have high throughput because we partition the problem into segments, and these are handled sequentially and farmed out, and then we bring the results back together and return an answer. But we could still exhibit poor response time. Right, so several processors are working together to solve a particular problem. Each segment takes some amount of time. So the total response time is time times the number of segments you broke this into. This means we could potentially process a large number of transactions coming in because we split it up and farmed it out to whoever is available. But that relies on having processes available. And that could result in a single response having a poor response time. And we could instead imagine a single processor system that processes requests sequentially. And if there are few requests, it's going to have better response time than the pipeline system, than the one that's broken up, because there's no latency in servicing that request and bringing it back together. But it might have poor throughput under heavy load because we have to wait for each person to be finished before we solve a second parallel person's request. All right. Here's one about reliability and the different reliability measurements. All right. We're building a new web store. Then we're going to unseat Amazon and beat them up for good. We've come back with figures saying that to accomplish our goal, we need an availability of at least 99%. Probability of failure on demand of less than 0.1, and a rate of fault occurrence of less than 2 failures per 8-hour work period. So as a reminder, availability is our uptime divided by the total time of observation. So if we have 1 day of observation, 24 hours, we were up for 23 hours. Our availability is 23 divided by 24. Probability of failure on demand is the likelihood that if you make a request, it's going to fail. So it's the number of failing requests divided by the total number of requests made. Rate of fault occurrence is the number of failures divided by the time in operation. So it gives you an idea of how often the system is going to fail. And so that's why you see here at less than 2 failures per 8-hour period, right? So we've been testing for a week, 7 times 24 hours. During this time, 972 requests were served to the page. It failed 64 times. 37 of those resulted in a crash. The remaining 27 resulted in incorrect totals. And when it crashes, it takes 2 minutes to restart. All right. So let's calculate a few things here. See if we meet our goal. First of all, what is our rate of fault occurrence? Okay. We want a rate of fault occurrence of less than 2 failures per 8-hour work period. So how are we going to calculate this? Right? Well, what we need to do is need to know how many failures, and we need to know how much time, and we need to then convert that down into 8-hour work periods. So how many failures did we have? Well, we had 64 failures. It doesn't matter whether it's a crash or an incorrect computation. For rate of fault occurrence, we count all of this, right? So 37 plus 27, 64 failures over the time period. Now, the time period was over a week, right? So we know we had 64 failures in over 168 hours, 7 times 24. That works out to 0.38 an hour, which works out to 3.04 per 8-hour workday. Okay. Now we do see that's bad right away. That's violating, that's greater than 2 per 8 hours. So our rate of fault occurrence is not good enough yet. What's our probability of failure on demand? Right, so that's our number of failures, 64, divided by the number of requests, 972. Right, that's 0.6066. That one's fine, that's less than 0.1, we're great. What's our availability? Well, for that, what we need to know is our uptime and our total time in service. We know our total time in service already, that was 168 hours. How much were we up during that? Well, we had 37 crashes. Now for availability, we only look at crashes because those are the things that bring the system down. We had 37 with 2 minutes to restart. So 37 times 2 is 74 minutes, right? So we are down for 74 minutes of 168 hours, right? So that works out to about 10,089 minutes. So we're down 0.7% of that time. Our availability is 99.3%, right? So to calculate that, that would be 10,089 minus 74 divided by 10,089. That works out to 99.3%, which means our availability is good. We're above 99%. Is the product ready to ship? No, because as we said, the rate of fault occurrence is not good enough. Right, so we need to improve the system. Let's do one more and then we'll take a break after that. So this is our system level testing. We have this airport connection check. This was also one of our exercise sessions. So, for the look back at those, look at the work you did during those, because that's good practice for the exam. We have this airport connection check that's part of a travel reservation system. It's intended to check the validity of any single connection between two flights. So if the arrival airport of flight A differs from the departure airport of flight B, the connection's invalid. If the departure time of flight B is too close to the arrival time of flight A, the connection is invalid, and so on, right? If the airport doesn't exist, the connection is invalid. So we have this function, right? It takes in two flights and it returns a validity code. A flight is a data structure that consists of a flight code, which should be a string with 3 characters followed by 4 numbers. There's an originating airport code, which is a 3-character string. There is a scheduled departure time and a universal time. There is a destination airport code, also a 3-character string, and there is a scheduled arrival time, also in universal time. Each flight is this data structure with its own, of course, its own data filled in for those fields. We also have a flight database where each record contains an airport code as the key with the airport's country, as well as the minimum connection times, which is an integer, the minimum number of minutes that must be allowed for a flight connection. It returns a validity code. 0 is okay, it's valid. 1 is an invalid airport code. 2 is a connection that's too short. It violates that minimum connection time. 3 is for flights that don't actually connect, like the flight A does not land in the same location as flight B takes off from. And then there's a 4 for any other errors that we have. If we have malformed input, if we have any other unexpected error, that's going to give us a 4 back, right? So what we have is really 5 different responses we can get from this. 1 is for our normal happy path. 4 of those reflect error cases. And what we want to do is we want to perform this category partition method. So we want to identify our choices based on these input parameters. For each choice, we want to identify different input values for that choice that will lead to different outcomes. And then we also want to come up with a few constraints to help limit our combinations. So this is a little simplified, but it fits on the slide. For the exam, there will be a question on category partition method, but it will be a smaller question. Again, I gave a longer one for the practice test, because if you can do the practice test, you're going to be fine on the real exam. So if you think back to when we talked about system testing, we have this process for each of the independently testable features surfaced by the interface. We want to identify its parameters, which can be explicit, those passed in, or implicit, like we have a database here. And that's also an input because its contents affect the outcome we get. Each of those can be manipulated in many ways when we're testing. For each of those, we want to identify a set of choices, which are aspects of that input you can vary and that can have some impact on the outcome of testing that function. For example, if the input is a data structure, our choices might include fields, the data structure that impact the outcome of the function. If the data structure is read from a file, then we might also look at things like the status of a file, whether it exists, whether it's corrupted, and so on. You cannot exhaustively test a function, so instead we partition this input space. For each of those choices, we divide it up into broad categories of input, these partitions that can trigger different outcomes. And we discussed some methods of partitioning during class, but often this is just taking a look at the different output you can get and seeing if you could trigger it, or seeing if you could trigger some kind of erroneous behavior, cause an exception to be thrown, cause an error message to be displayed, and so on. And then once those representative values are chosen, we could start forming test specifications by choosing a value for each of these choices. We're not going to get that far in this exercise. For this exercise, we just want to come up with our choices, our representative values, and we could also apply some of these constraints, though I don't actually have any in the slide for this, so we don't necessarily have to worry about that either. So in this case, just the choices and the representative values. Yours could look different. There's a bit of subjectivity in this, but you do want to try and be fairly thorough, okay? This function has two explicit inputs. It has an arriving flight and a departing flight, so flight A and flight B. It also has the database as an implicit parameter. For each of those, we can make certain choices. So for these are data structures. This flight data structure suggests to us 5 choices: the flight code, the originating airport code, the destination airport code, the scheduled departure time, and the scheduled arrival time. Now, those are not necessarily the same choices for those, they're the same representative values for those choices for both of these, right? Both of these have the same choices, but these have slightly different representative values because they interact with each other, the 2 different parameters. The database also has an airport code, airport country, and minimum connection time. Those can influence the outcome as well. So those are also important, okay? So for the arriving flight, what can we do with it? Well, the flight code, it could be valid, right? Perfectly valid flight. It could also be something that's malformed. And we don't necessarily have and mentioned flight database as well. But, if there is one, maybe we have a database of flights somewhere or a list of flights somewhere, and we could say, hey, it's not in that database, right? So that's being a little speculative. On any similar questions, state your assumptions carefully, right? Just to make sure it's clear what you're thinking here. So in this case, the question did not say there was a flight database, but my sample answer does assume there is one somewhere. So I would have it's, this fitting everything on the slides a little harder. I would have somewhere an assumption, just some assumptions at the beginning, and I would say, hey, I assume there is a flight database or something like that, okay? But in any case, you can have a malformed flight code because we said explicitly earlier that the flight code is 3 letters followed by 4 numbers. Anything that's different from that is malformed. So at least malformed and valid, but you could go even more thorough if you chose to. The airport code, malformed or valid, of course, because it's a 3-character string. And then we do have a database of airports. It could not be in that database, right? And that's going to lead to an error. Our departure time could be a legal one. It could also be something that's malformed. We pass in something that's not a valid time. We could pass in something that's out of a legal time range. So we say that it's, 2,500 hours or something. Destination airport, same thing as originating airport. That could be something that's not in the database. That could be a valid one. That could be a malformed one. And then scheduled arrival time, pretty similar. It gets a little more interesting for flight B, the one that takes off. And then we have to make sure that we can connect to, right? So once we get into the airport code, we need to make sure that this second flight, the departing flight, leaves from the same airport that this one arrived at. So here, we can add an additional option here, right? Our valid becomes same as the transfer airport, but it could also be one that's a valid airport, but differs from the airport we're transferring from, the destination one for flight A. Let's see, our departure time now gets it more interesting too. We have our errors from before. We also have a few more. What if our departure time is before the scheduled arrival time, which we're going to call TA? If it's before that, that's also an error. That we can't make a connection if the second flight takes off before this one arrives. We could have a departure time between the arrival and the minimum connection time, which means it's an illegal flight because the connection time is too short, right? And we can have one that's equal to the flight time or the arrival time plus the connection time. So exactly at the point where we have meet the minimum connection time, that should be fine, but our software might not handle it correctly. So that's one of those boundary cases. And then a valid, normal, very happy case where we have plenty of connection time. We have more than is the minimum connection time. For the database, we could have an airport code. We could leave something blank. We could have a valid one. We could have one that's not a 3-letter string. For the country, we could have something that's not a valid country, that is valid, that's blanked, or that's malformed in some way because we're using 2-character country codes. And for the minimum connection time, we could have some valid number. We could leave that blank. We could have something. You should probably be more specific. I could have put something better here. Looking at this now, I actually think, hey, I should put negative here or something like that, right? Negative or 0 are going to be invalid. So be clear on that. Malformed, not a valid time, and then some valid connection time. So 15 minutes or something. Do you have any questions on this process? On this answer, on anything? Everyone's still good and with me so far? All right, let's go ahead and take a break now. It's 11:08. Let's come back at 11:20, and then we'll resume with the next question. And in the meantime, feel free to throw a question into the chat if you have anything. All right, let's get back into it. So a lot to cover. Like I said, we're almost certainly going to go over our time today, and I'll just continue until we finish everything. But it's a recording, of course. So if you have to go at some point, make sure you catch the video later on. All right. So now we move on to combinatorial interaction testing. Combinatorial interaction testing is where rather than trying to cover all combinations of values to all of the different choices in system level testing, what we do instead is we try and cover all values for pairs of variables. This lets us, if we choose values carefully, cover all these pairwise combinations of inputs in a much smaller set of test cases. So for example, we've got a system here where we have 6 different choices. Allow content to load, notify about pop-ups, allow cookies, warn about add-ons, warn about attack sites, warn about forgeries. Each of those, we have a set of representative values. If we wanted to cover all combinations of values for all variables, which is what we would usually start with looking at with these test specifications, we'd have 3 times 2 times 3 times 2 times 2 times 2 combinations, or 144 test cases. So allow, yes, 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 allow, yes, yes, no, and so on. However, in combinatorial interaction testing, what we do is we create this covering array. A covering array is a set of test cases that covers all combinations of values for all pairs of variables. So rather than looking at all combinations of you, with you, with you, with you, with you, and with you, we take 2 of these and allow content to load, notify about pop-ups, and we make sure we cover all combinations of those 2. Then we bring in a third variable and we add in and we try to choose values for it. So we cover all, again, with a small set of test cases, cover all combinations of allow content to load and warn about add-ons, allow content to load, notify about pop-ups, warn about add-ons, and so on, and continue until we cover everything. So if we want to do this, what we do is we start with the 2 variables with the most values, and then add additional variables one at a time. So we'd start with allow content to load and allow cookies. They each have 3 values. We'll start with those and come up with all combinations of values to those, right? That's a total of 9 test cases. Now, we then would choose values for the rest of these 4 variables one at a time so that we cover all combinations of values with the existing variables, without adding any additional test cases, if at all possible. And if we choose these values carefully, we can do this in 9 test cases, 3 times 3 test cases, or however the number of representative values for the 2 choices with the most values. So here's what this looks like. Your specific answer can vary because you might choose values in a different order or differently, but in any case, you should within 9 tests be able to cover this one, right? Because the 3 values for allow content, 3 values for allow cookies. Here's all combinations of those: allow and allow and restrict, allow and block, restrict, allow, restrict, 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 block, block, allow, block, restrict, block, block. Now we would take the next one, pop-ups, as our next variable, and we would start one by one, including choosing values for it to cover all combinations of pop-ups values with allow contents values, pop-up with allow cookies, right? And then we'd have all pairs of these 3 variables covered. So allow and yes, allow and no, allow for this and yes, restrict and yes, block and yes, restrict and yes for this, and block and yes, and then of course for no as well. And then we have a dash. This dash means we don't care. Once we fill these in, we're left with one of these where it doesn't matter. We've already covered the combinations, and so we just put a dash here to say it can be yes or no. We just don't really care. It doesn't matter. Now, as you add additional variables, some of those dashes are going to get filled in because you need a certain value. So then we bring in add-ons, which has 2 values, and we try and then pick values for it to cover all combinations of add-ins with allow content, add-ins with allow cookies, add-ins with pop-ups. So here we have yes and yes, no and no. So those two are covered. Yes with allow, yes with restrict, yes with block, right? Then, no with allow, no with block. Can it be allow? Yes, yes. You can pick, you could have selected values in a different order, right? The important thing is to cover all combinations of any of these two variables, right? So you could have done allow, no, no, and that would be fine. That would have covered the combination of no with allow and no with allow for this one. And then, no for add-ons with allow and no for with allow and then no with no. So you would just need your other test cases would be different. So because you cover those combinations with different different test cases. But each row is a test case, and you just want to make sure that you've covered, if you choose two of these choices, if you choose allow content and pop-ups, you've covered all combinations of allow, restrict, and block with yes and no. Does that make sense? Any questions on this? Right, and then you just keep going until all variables are in place. And as you do, you'll fill in some of these don't care values. All right, next is exploratory testing. When we do exploratory testing, it is guided by a set of these tours. Each tour describes a different way that we can think about the system that we're testing. And it gives you ideas for how you should act while you explore the functionality of that system. So for example, the antisocial tour is one where you go in and you just try to break the system, right? You fill in ridiculous values. You try and compromise its security, right? Or the couch potato tour, you leave things blank and see how the system handles default values or blank values, right? But what we want to do in this question is describe one tour, and for that tour, consider a banking website and describe 3 actions we take during exploratory testing for the system based on this banking website and based on the tour we've chosen. So as an example, one of these tours is the supermodel tour. The supermodel tour is focused on testing the GUI of the application. It's not concerned with functional correctness. The correct data is displayed on the screen. Rather, it's concerned with the visual appearance of the graphical interface and whether that visual interface is correct. It focuses on whether graphical elements display in the correct locations and without glitches like rendering errors or rotation or size issues. And it looks also at timing aspects of the GUI, like how long it takes for a mouse cursor to move or for text to update on the screen, for new screens to be drawn, and so on. We can look for typos in displayed text, or we can look for usability issues or suggestions on how to make the system easier for new users to learn how to work with, right? So for the supermodel tour, what are 3 actions we could take for the banking website? Well, one thing we could do is we could click on a drop-down menu, for example, and make sure that menu displays quickly, and that when it does display, that all the required items are present and they're displayed correctly. The menu appears in the right location, and it doesn't cause any issues when it appears over other on-screen items, like it doesn't make on-screen items jump around. Nothing like there's not weird floating text somewhere. Basically, that this drop-down menu displays appropriately and correctly and quickly. When we select an account, we can ensure that the account information is displayed on the screen, that displays in the correct location with like our name and account number and things like that. And that this information is easy for a user to see if they're looking for it on the screen, like it's a good font, we make appropriate color and size choices, and so on. And then when the user goes to edit personal information, we could ensure that that existing information is displayed on the screen and that the edited segments are refreshed and displayed to the user correctly and quickly. Next, we are looking at unit testing, okay? And we've got a simple method. It takes in 2 doubles and it displays the max of them, whichever one is larger. It's pretty simple functionality, right? And what we want to do is come up with 4 JUnit test cases for this. It doesn't matter what they do, it doesn't matter what functionality, but good use of assertions, reasonable usage scenario, maybe see if you could potentially trigger an error, see if you can do that. So just think about testing this a little bit. And what would you do? Now, these test cases, 2 of these I did include multiple assertions. That's not necessarily a better practice is to have 1 assertion, or if absolutely necessary, a small number of related assertions on a test case. But I include a couple just to show different ways you could show this answer, or that you could test this function. So 4 scenarios here. First, there's one where A is larger than B, then one where B is larger than A to make sure that that works as you'd expect. One where they're equal to make sure nothing weird happens when they're equal. And one where we try negative values just to make sure negative values work as you'd expect, okay? So first one, A is larger. A is 16, B is 10. We expect the answer to be 16. We get the actual answer, and we assert that the actual answer should be 16. We also assert that, it should be larger than B, that A is the larger answer. Same for this one, it's just we swap everything. B is now 16. We can still compare expected to actual, and we say the actual answer should be greater than A. They're equal. We again check that the expected answer is what we wanted. So if they're both 16, the answer should be 16. Shouldn't be anything weird here. And then both negative, -2 and -1. We expect -1 to be the max value. It's the greater value here. We could include an assertion to check whether the answer is negative. Again, I'm just throwing some extra things in here just so you can see different ideas. But the actual answer, of course, should be -1, and so we check that. All right. Any questions? Everyone still good? All right. We can just keep on rolling through this then. So we have carefully and we have thoroughly come up with a collection of test cases based on our requirements, based on our intuition about how the system should work, and we run those. And once we have run those, we have discovered we achieved only 60% statement coverage. And we're surprised and we're sad by this, and we're going to go cry into our beer because, well, we thought we were done testing and our statement coverage isn't great. Because we expected the answer to be closer to 100%. So what are 2 things that might have happened to account for the fact that 40% of this code was not exercised with the requirement-based tests? Now, there are several reasons for this, possible reasons for this. And the most obvious one is that we did a poor job in picking our test cases. Now, of course, since we assumed we did a good job and we said we were thorough, that might not be the case. So we could be other things. We could be missing requirements. The requirements document could be incomplete. And when we went to build the system, we had to come up with more functionality ourselves for which we don't have requirements, right? Informally, we filled in those cases when we developed the code, but the requirements, we never wrote formal requirements for some of this code. And so when we develop our test cases from an incomplete requirements document, that's going to naturally lead to poor code coverage. We could have large amounts of dead code or inactivated code. That's code that we've written, but there's effectively no way to call that code, especially from a system level, right? If most of our test cases are system level test cases, we might have code that cannot actually be called. We put it in there speculatively, or we inherited some code and we're just not using all of it. And so that code's not going to be covered, right? If we have any, there's all sorts of reasons there why we have unneeded code that can make it into the software, and your test cases will not touch it because you can't call it. There could also be error handling or other valid optimizations in our code, right? We might have done some very strict error handling in our code, and it accounts for situations that actually cannot be called. There's just no way to actually trigger those errors, or trigger that error handling rather. And so we just cannot actually get to it, right? You might even have a case where a programmer built in like lookup tables for various functions or things like that, and you're just not calling that, right? So you might have very well have code that just doesn't get called, that cannot be called, that accounts for error handling that you cannot actually trigger. And that's fine and normal, but you have to look at the code and understand why that's the case. In general, though, should you expect 100% statement coverage from your requirements-based tests alone? And the answer is no. Like, there's always going to be some reason why we have code that isn't covered by requirements-based tests. We're always going to have some cases where we have to add code that we just didn't think to write requirements for. We might have helper functions. We might have file IO. We might have database connecting code, operating system interfacing, all sorts of things that your requirements just aren't really concerned with, like low-level helper code that you need to write, that you need to have, but you don't have requirements for it. And so that's not going to be covered in all likelihood. You're going to have error handling and exception handling code that is very difficult to trigger, if not impossible to trigger, and you might not have covered that with your requirements-based tests. Debugging code, other optimizations you've made, and it's highly unlikely that you're going to get close to 100% coverage through black box, through requirements-based testing alone. That's why we have structural testing, is to help augment your test suite, help fill in some of those gaps. Now, some structural criteria like MCDC also prescribe goals, test obligations. They're impossible to satisfy. And what are two reasons why a test obligation might be impossible to satisfy? Well, you might call outright for an impossible combination of conditions within a decision statement. Like if you have a statement that is, if A is less than 10 or A is greater than 10, well, the both of those can't be true, right? Concurrently, it's going to be one or the other. It's either less than 10 or greater than 10. Can't be true at the same time. So you might just have conditions that you cannot combine in the right way. You also might have performed other defensive programming practices. As a result, you have error handling code that cannot be triggered, right? And you just can't get to it and call it. Or other unreachable or unused code that cannot be called directly or cannot be reached through normal execution paths. Again, this is especially true at system level test cases. Unit tests can, of course, dive deeper into this, but you might have code that just is in the system but is not actually being used. You've implemented for future use and you haven't integrated it yet, or it's just not, or you imported code and just aren't using all of it, and so on. All right. Next, we have a short method here. Find max takes in 3 integers, finds the max of those 3, and returns it. Great. We want to draw a control flow graph for it. Then we want to come up with test input that gives us statement coverage, input that gives us branch coverage, and then input that gives us path coverage. The difference here, of course, is path coverage means that we have 2 if statements basically. We will need a case where that's true and this is true. This is true and this is false. This is false and this is true. This is false and this is false, right? So we care about how those all connect together. For statement coverage, we just want to cover all the statements. For branch coverage, we need this if to be true and false and this if to be true and false, but we don't care about how they combine. So here's the control flow graph for this. We can write the line numbers in here. So line 2, there's this if statement. In line 3, if A is greater than B. If it's true, we go to line 4. Otherwise, we go on to line 6 here in the else. From there, we go to line 7. If C is greater than temp. If it's true, we run line 8. And then go to line 9. If it's false, we go straight to line 9 and we return the value of temp. So there's our control flow graph. Pretty simple. Statement coverage means that we've covered every single block in this. Branch coverage means we've covered every edge. Path coverage means we've covered every possible way to get from 2 to 9. All right, so statement coverage. A couple test cases here. 324 and 234. Those cover certain paths through this. So 324 takes us through here, right? So when we get to the if statement, we compare A and B. A is greater than B, so we go to line 4. We go to line 7, right? In line 7, 4 is greater than temp, which is 3, so we go to line 8. We set temp to be equal to 4. We return 4. Our second one is going to step straight down here and cover 6, which was what we were missing. Right, so here A is less than B. So we go in here and we set temp to be equal to 3, compare it to 4, and we return 4. You'll notice here that we have not achieved branch coverage because we have not covered the false for line 7 out of here, right? So we need an additional test case to do that. So we'll keep 324, and we'll add one that's 341, okay? So for that one, that's going to give us this path through. We get to line 3. A is less than B, so we execute line 6 to set the 4. We get down to line 7. 1 is less than 4, so we take the false edge and we return 4 as our answer. All right, so what does branch coverage do in terms of paths? Well, it gives us true, and it gives us false and false. That's not enough for path coverage, where we also need true and then false. And we also need false and false. Oh no, we got, we need true, or we need true and then false, and we need false and then true is what we need. All right, so for path coverage, we'll just come up with 4 test cases. Those test cases cover, 425 covers true and true, right? 421 gives us true and false. 234 gives us false and true. And then 231 gives us false and false. And that's going to cover all 4 of the ways we can step through this control flow graph. Okay. Now we also want to modify this short little program to introduce a fault such that even path coverage would miss this fault. So what can we do with this? I mean, really what it depends on here is our test inputs, right? You can pass an input that achieves coverage without triggering a fault. Those are 2 different things. Stronger coverage can help reveal faults, but it doesn't ensure it. So what's one thing we can do? Well, maybe we could here use as A equals B plus 1. So we're going to introduce an arithmetic operator here instead of A is greater than B, right? And then that test input from before won't reveal that fault. It would only do so if A and B were quite similar. For instance, in our original, if A is 3 and B is 1, this will work, right? But if A is 3 and B is 2, then they're going to get the same outcome. They're going to be equal, which means that we're going to go to false, which is going to potentially introduce a problem here. So it all depends on which test input we pick. You can pass an input that gives you the coverage without triggering the fault, as these do. So these do not trigger this fault, but they do give you path coverage. Path coverage doesn't guarantee all faults are detected. It still depends on what input you pick, right? All right, so next we have another little bit of code, and we want to identify all of our def use pairs and then write some test cases to achieve all def use pair coverage. So def use pair is a link between the line where a variable is defined and the line where that definition is used without it being redefined. So for instance, in line 1, n is defined, and then n is used in line 4. It's redefined in line 5. So when we go through the loop again and get back to line 4 again, we also have a pairing between line 5 and line 4 for n, right? All def use pair coverage means we need to write test cases to cover all def use pairs at least once. So first we want to come up with our def use pairs. And then what we want to do is come up with test cases that cover all of them. So start with the pairs. And here we can come with these. So we have 4 variables. A is our array, we have n, which is this int, we have v and d. So a is defined in line 1, and it's not redefined anywhere, but where is it used? It's used in line 6, it's used in line 8, and it's used in line 9, right? So we want to cover, we want to have test cases that cover all combination, or that cover lines 1 and 6, 1 and 8, 1 and 9 at various points. For n, we define it in line 1 initially. It's used in line 4. It's used in line 5. Then it's redefined. That new definition in line 5 is used in line 6. It's used in line 8. It's used in line 9. We come back through. It's used in line 4, and it's used in line 5. For v is defined initially in line 2. It's used in line 7, where it's redefined. If we skip the loop, the definition in line 2 is used in line 11. Otherwise, this definition in line 7 is used in line 11, and it's also used when we come back through in line 7 again. Then for d, it's defined in line 3, and it's used in line 6. It's redefined in line 9, and it's used when we go through the loop again in line 6. Okay, so that's our def use pairs. Any questions on that? All right, now we want to come up with test cases, right? And so 3 test cases are sufficient to do this. First of all, we have 1, 2, 3 for our array, and the number 3, that's going to cover these def use pairs, right? So, you know, we pass this in, it's going to iterate over the loop multiple times. It's going to basically cover a lot of these in one time, but it doesn't have any inflection points, right? So it doesn't have anything that's going to give us a true in line 6 and execute line 7. So line 7's not been run here in this first test case. To do that, we need one with an inflection point, which means that we need to we can flip 1 and 2, and that's going to give us one of these. Basically, we have an array that's not in sorted order. So that's going to go through, that's one inflection point. That's going to cover, in addition, the 2 and 7 and 7 and 11 for v. We're still missing those 7 and 7 for v. For that, we need at least 2 inflection points, which means we need to iterate through this multiple times, and we need to get a true for line 6 multiple times. So this array with 2, 1, 2, 1, 2, or we change. So the array is not sorted, and we alternate between values a little bit, between lower and higher values. And that's going to give us 2 inflection points. And that's going to cover that additional 7, 7 pair, right? So the important thing in this is to make sure that you look carefully, make sure that your test cases do trigger the set of lines that you're expecting. Be careful with loops, because a lot of def use pairs require more than one run through a loop, especially the 7, 7 needs at least 2. And both of those need to be these inflection points to give you a true in line 6. All right. Next is mutation testing. So we've got a function here. This B search, or binary search, takes an array, the value you're looking for, and a start and end. And it's going to check if it's found what you're looking for, and otherwise it's going to recursively search. And we want to come up with some mutations for this, right? So first of all, we want to come up with an equivalent mutant using any of the mutation operators we discussed in class. I mean, an equivalent mutant is one that no matter what will give you the same outcome. So what's one that can do it? Well, we could shift an end block if in this else we shift the bracket up and return mid is now after it. That's going to always give us the same response, because by the time you get down to this else, well, you're going to return mid, right? So that shift is going to give us the same response for every test case. Creating an invalid mutant. So this is one that won't compile. That's usually pretty easy. And statement deletion is a very quick path to that. So if we just delete a line from this, well, we have an unadjusted number of brackets. We got an else if without an if at the front. That's not going to compile. It's not a valid mutant, right? So a valid mutant compiles, and an invalid mutant doesn't. Now we can have mutants that are valid, so they compile, but they're not useful to us. They don't really tell us anything when we test. What that means is that all test cases or the vast majority of test cases that call this method will fail for the mutant and they'll pass for the original. If basically any test case can detect a mutant, that mutant isn't helpful, right? That mutant doesn't tell us anything. It doesn't give us a way to improve our test suite. It doesn't suggest how we can add more test cases. It's just trivially detected, right? So it's not great. What's one thing we can do? Well, relational operator replacement at the beginning, if we change n less than equals start to n greater than start, that means that as long as end is not equal to start, then this mutant is going to fail, right? It's pretty likely that your test cases don't have end and start equal to each other. So this mutant will be trivially detected. Now, finally, we want a useful one. This is one that actually might be a little subtle, that might help us when we're testing. And what we're going to do is replace one constant with another. Right here, we have mid plus 1. We're going to change that to mid plus 2. Okay? This is not always going to fail. What this requires is input that triggers that specific else if, right? And may still return the right result as long as it doesn't skip the correct array entry. Because what we could do here is we could skip an important array entry, right? If we don't skip anything important, we won't detect it. So we need to come up with slightly more specific input to detect this particular fault, which means this is the exact kind of mutant we hope for. It's the one that's going to actually help us when we're testing. Okay. All right, next, we're looking at the search-based test generation, right? And we have these meta-heuristic search techniques. They can be divided into local and global searches. And we want to define what a local and a global search is. We want to contrast the approaches a little bit and what are the strengths and weaknesses of each. And we want to choose a search algorithm and briefly explain how it works, okay? State whether it is a global or local search and explain why it belongs to that particular category. So, first of all, what is a global search and what is a local search? So local search techniques, they formulate a solution and they attempt to improve that solution by making small changes to it, by looking for better solutions in its local neighborhood, which are the possible solutions we form by making one tiny little change. Global searches freely sample from the entire space of possible solutions. They typically form more than one solution at one time. So they form a population of solutions and they freely change those solutions by moving them in any way throughout the search space. They don't restrict themselves to making one small change to the existing solution. Now, what are the strengths and weaknesses of each? How can we contrast these? How are they different? Well, local searches are often very fast. They're very easy to implement. They're very easy to understand conceptually because they take one solution, they make a guess, and they just try to improve that guess until it's good. But the downside is they depend strongly on that choice of initial guess or initial guess. They can easily get stuck in different local optima where they find the best solution possible given the local neighborhood, but not the best for the entire search space as a whole. And this weakness can be partially overcome by allowing restarts, but not completely, because you might make a bad guess more than once. Global searches are often slower because they're iterating on a whole lot of solutions at once, and they are more complex, so they have more overhead. They're harder to implement and harder to understand, but they have no problem with becoming stuck as they try more than one solution at once. So sometimes or actually often, they can return better solutions because they don't get stuck. But because they're slower, they might not find as good of a solution given a certain time period to work with in a certain time budget. To give an example of one technique and explain how it works, we can look at simulated annealing. Simulated annealing is a local search. It's probably the most famous local search. What it does is initially a solution is generated at random, and then it tries to improve it. During each round of the search, you pick one of its neighbors. So, again, a neighbor is a slightly different version of the solution. It's making one change. So if we pass in an integer to a method, we might increment or decrement that integer by a little bit. So we choose a random neighboring solution, so something that's just slightly different, and we see if it's better. If it is better than the current solution, it becomes the new solution, and we move on. If it's the same quality or worse as judged by our fitness functions, then we're going to ask the probability function to decide for us whether it becomes the new solution. So at some probability, even if it is worse than our current solution, we'll go ahead and make it our solution anyway. Initially, as the search starts, it's far more likely to choose a bad solution as the new one, just to allow some big rapid jumps through the search space. This lets it avoid becoming stuck. Over time, it becomes less likely to accept worse solutions. So over time, it becomes what we call a hill climber, where we will only take a better solution. But at first, it's going to quickly jump around the search space, and then it's going to stabilize a little bit. That lets it avoid becoming stuck in these local maximas. This is a local search because it manipulates one solution at a time, and it focuses on the local neighborhood when making changes. All right. Now we're going to move into finite state verification. Let's say that we are verifying a model of some system, and it comes back and says the property is false and gives us a counterexample, as you've seen in your homework probably, right? And it's a property you expected to hold true, so that's indicating there's a potential problem. So when you see this counterexample come out, well, what happened and what are the follow-up actions you would take? Now, this tells us that a property we expect to hold is not held by the model. So that implies one of three things has happened. Something is wrong. Now that what is wrong can be the model. So there could be an issue with the model. The model was made by interpreting the requirements, and there could be a mistake we made in that interpretation in our model. So fault in the model code, bad assumptions made, some incorrect interpretation of the requirements. So our model is broken and we need to fix it. Or it could be a problem with the property we wrote. The property might not be formulated correctly. It might not say what you intended it to say. These formal logics are very specific, right? And it's incredibly easy to write a property that isn't actually what you meant it to be, right? So it very well could be that your property is incorrect. Third is that there could be an issue with your requirements themselves. Your requirements might be incorrect, they might be unclear, or they might be incomplete. So it could be any of these three things. What you do about this depends on which of the above are true, and you need to figure that out. So you need to look at each of these three things and find the source of the problem and correct it. If the model is incorrect, locate and correct the fault, run this again and see if the property is now met. If the property is incorrect, stare at it for a while, see if you can reformulate it. And if the requirement is incorrect, that needs to be reformulated and refined too. And then you need to rewrite your property and potentially your model to match the change to the requirements. Fixing the requirements might unearth changes you need to make in the model as well to match, so it matches what you did to the requirements. Okay. Now, we have a couple more questions here about this finite state verification. As a quick refresher first, we have some temporal properties. G implies that something is globally true at every state. So if we say that G of P, that means that this property P is going to be true, and it's going to remain true for the future. FP means something that is currently, that something will eventually become true. It could be false now, it could be false for 10 steps, but at some point in the future, it's going to become true, at least for one state. X means that something is going to happen, this is going to be true at the very next state on the path, right? So if we're in state 1, as soon as we transition to state 2, this is going to become true. F and X are different. X is at some unknown point in the future, whereas X is specifically at the next point in the future, okay? F means we don't know when it's going to happen. It could be in the next state, but it doesn't have to be. X very specifically means the next state. U means until. It means something is going to be true until the second half of it becomes true, right? So P must be true now, and it must be true until Q becomes true, at which point P can no longer be true, or P is allowed to become false. It can remain true if it did once, that's fine, but it's allowed to become false once Q becomes true. And then for CTL, we have these two path operators. We apply to one of these above ones. So A is saying that all paths branching from this point, something is going to happen. So AGP means that P is always true no matter what timeline we're on, no matter what path we take, branching out from this point. E means at least one path for some path. Something doesn't have to happen along all paths, but at least one future timeline occurs where this thing can occur, right? So if we say EFP, we're saying that, well, there is some future where eventually P becomes true. It doesn't have to be in every future. There could be a future where P is always false, but there must be some possible timeline, some sequence of transitions we take where P becomes true at some point. Okay, so let's use these. This should be question 15, but that's fine. We have a traffic light controller with pedestrian crossing, a button to request right of way. This is a very heavily simplified model, right? The light can be red, yellow, or green. The light can be wait, walk, or flash. The button can be reset or set. And we want to come up with some properties for this. So first, we want to formulate a safety property in CTL. A safety property that's most of our properties. This is where we say something must happen or something must not happen. And we prove that that either does or does not happen. So for instance, we could come up with one that says that this AG in all paths globally, it must be true in the parentheses, that pedestrian light equals walk implies traffic light is not green. So we're saying is that the pedestrian light cannot tell me to walk while the traffic light is green. It's a safety property. We're saying something bad must never happen. So this must not, this must never be violated. The traffic light will never be green when pedestrian light is walk. Right? Next, let's come up with a liveness property. A liveness property is a fairness criteria that's saying something we want to happen will eventually happen. Right? So what's one look like in this case? Well, here we go. We have G, traffic light is red, and button is reset, implies that eventually the traffic light will be green. So what we're saying is that, if the light's currently red and reset has been pressed, or the button is set to reset, well, at some point the light's going to transition to green. Right? The pedestrian's not asking to walk. At some point in the future, the traffic light will become green for us. That's a liveness property because we don't know when it's going to become green and we don't care when it becomes green. We just want to make sure it does eventually become green. Okay. Now let's come up with a trap property to derive a test case to exercise a certain scenario. So a trap property is what we use to generate test cases. This is where we take a property that we expect to hold over the model, we negate it. So we actually say, hey, this property can't hold. And the model checker will come back and give us a test case. It'll give us a set of input steps that show the property can be met. We can then run those input steps in the real system and compare the result to the model to see if the model and the system prescribe the same behavior. It's a nice way to make sure that the real system does meet your requirements and that it matches what the model said should happen. So what we need to do here is first we need to formulate the property in a temporal logic and then translate it into a trap property, right? So we're saying pedestrian obtains right of way to cross the road after pressing the button. What does that look like in temporal logic? Well, in temporal logic, we're saying globally, if button is set, that means the pedestrian has clicked the button, then eventually the pedestrian light will say walk, okay? This means no matter what happens, if this button is pressed, eventually the light will turn to walk so the pedestrian can cross the street. This is a liveness property. We're saying something will eventually happen. We're not saying when it has to happen, just that it does have to happen. So what we need to do now is turn this into a trap property. To do that, we negate it. So we say globally, it's not true that this will happen. We're saying that it's never the case that if we press set, eventually the light will become walk. because this property does hold over the model, that if you press set, it will become walk. And when we said it's not, that means the model checker will come back and give us this counterexample. And this counterexample can then again be run on a real system to show that it does the same thing the model does, and that they are in fact in conformance, or if it doesn't, then they're not in conformance and there's a problem. One more of these. Now, the practice exam is heavy on this topic because it was the last thing we talked about, so I wanted to make sure you had some examples. The real exam will not have several questions on temporal logic. I'll just say that now. It will not have several questions on this. I'm just giving you bonus questions in the practice exam just to help prepare you. Okay, so we have a microwave controller. The door can be open or closed. The button can be none, stop, or start. The timer can be 0 to 999, which is our remaining time to cook. And cooking is a Boolean, whether it's actually currently heating or not. Okay, so what we want to do is we want to come up with in CTL a case where the microwave shall never cook when the door is open. How do we formulate that? What this looks like is AG. If the door is open, that implies it's not cooking. So in all paths, it's always going to be true that anytime the door is open, it will not be cooking at the same time. Okay. In CTL, we want to say the microwave shall cook only as long as there is remaining cook time. What does that look like? Well, here again, AG is used, so always true. That cooking implies timers greater than 0, right? There's always time remaining as long as if we're cooking. In CTL again, if the stop button is pressed when the microwave is not cooking, the remaining time will be cleared, right? What does this look like? Again, we have an AG. It's always true on all paths that whatever is within the parentheses is true. If the button is stop and we're not cooking, that implies that in the next state, the timer will become 0. The only tricky thing here is that next state part, right? You can't expect things to happen concurrently necessarily if you have to induce a change. If something is going to change as a result of the current state, that means it will happen in the next state. So when we press the button and it's not cooking, it will clear in the next state. So in the next state, the timer will become 0. Okay. In LTL, we want to say it will never be the case that the microwave can continue cooking indefinitely. Okay. That indefinitely implies an F and eventually. So we're saying it's true that if we're cooking, then eventually we're not cooking. It's going to stop at some point. We're not going to be specific on when, because that depends on how long you're microwaving, right? It depends on all sorts of conditions, but it will eventually stop no matter what. And that's true. All right, here's another in LTL. The only way to initiate cooking will be pressing the start button when the door is closed and the remaining cook time is not 0. Right? So we're getting a little more complicated here. So what we're saying is that cooking is false until the following conditions are met, until the button is start and the door is closed and the timer is greater than 0. Okay, so door is closed, start button's been pressed, remaining cook time is not 0, but until that point, we're not cooking. Another LTL. The microwave shall continue cooking when there is cook time left, unless the stop button is pressed or the door is opened. Okay, so there's going to continue cooking until something happens. That implies, that implies we have to say something about what will happen in the future, right? So globally, it's true. This gets a little complicated, but if we're cooking and there's remaining cook time, then in the next state, we're either going to continue cooking or we're not cooking and the stop button was pressed, or the door is open. Okay. Now there's a couple different ways you could formulate this. You actually could use an until here. You could have, something like, you still need to have something about the next state, because like globally, it's not necessarily true that cooking is true until something happens. You might be not cooking for a while, then cooking. But you could formulate this probably in different ways, but this is, I think, pretty straightforward. If we're currently cooking and there is time, then we're either going to be cooking or something's going to happen to prevent it. And what can happen to prevent it is the button is stop or the door is open. Are there any questions? I've been babbling nonstop at you, so please let me know if there's anything. But in general, that is our review. I'm happy to answer any other questions if there are any, but I would just also say thank you for being a great class. I really hope this has been educational. I really hope this has been a good class and helpful and useful to you. That everything has gone smoothly, and like I absolutely, I hope you've learned something out of it. And thank you for attending. Thank you for coming to all these different lectures. So excellent. Thank you very much. And I will I'm going to be present for the exercise session this afternoon. There's no exercise plan, but if you have homework questions, if you want exam help, I will be around, for that. Otherwise, good luck in the exam next week. And let me know if there's any questions in the meantime. And have a great time, and I'll see you at some point in the future, hopefully once Corona finally ends and you're all back on campus. All right, cool. Any other questions before we're done for today? All right, then we'll stop there.